Okay, are there any questions from? Okay, so the topic of today is supposed to be twistors. So there are a few papers. So they're on different topics, but otherwise it's twistors. So I'll try to say something about these different papers. This is about D plus 4. This is an attempt to generalize to D plus 1. This one is, it's not quite twistors, but it's a version of the string at infinite tension. So if you like alpha prime goes to 0. With pure spin. And then this last one is getting the BRST operator from twistor. So they're all different subjects, but they seem to indicate that there's some relation between pure spinors and twistors. So let me start with just four-dimensional twistors. So once I go to 10, you can start to question if I'm doing the right thing, or maybe there's a better way to do things, but at least the four-dimensional super twistors, I think people understand that this is the best way to do things. So as I mentioned in my talk on Wednesday, these were actually developed in the 70s by somebody, Alan Ferber, who, I don't know if he gave up physics, but he didn't stay in physics. So he was from Chicago. I can't remember the name of his advisor. You know, the one who did periodic numbers.
Peter Freund.
Yeah, it was Peter Freundsten. So, in fact, this version of twistors is much better for describing the superparticle than x's and thetas. So as you'll see, quantization is just completely straightforward. So I spent my first lecture telling you how complicated it is to quantize a superparticle using Green-Schwarz. Using twistors, it's completely trivial. You just try. So what's a twistor? So in four dimensions, so in general dimensions, it's a pure spinor. But in four dimensions, a pure spinor is just a chiral or antichiral. Let's call it chiral. So just, since I may use 10 in four-dimensional notation at the same time, let me say small a is just 1 to 2. A dot. All you need to know is two-component spinor notation in four dimensions. So the conjugate momentum to lambda a, I'll call WA. And the conjugate momentum, this should be WA dot. So I'll call this, okay, let me try. There's always the question if you put the bar here or the bar here. I think I'll put the bar here. So the bar doesn't necessarily mean it's a dot, okay? The reason why I wrote it in this way is because these transform into each other under SU2, 2, which is just the same as SO4, 6. SO4, so these transform linearly under the conformal group.
So here bar means complex conjugation, is it?
So bar is complex conjugation, but it doesn't necessarily go with the a dot. Okay, so I'm writing W a dot instead of W bar a dot. Why? Because when I do an SU2 transformation, lambda a will mix with W a dot and not with W bar a.
But W a dot star is W a bar.
Yes, if you're in SO3, 1. So sometimes I'll use SO2, 2, which are independently real. But, yeah, and this signature, yes, they're complex conjugates. Okay, so before we get to super twistors, let's just understand what twistors are. So you can write all the conformal generators in terms of these. So I don't know how much people know about twistors. I guess I'm assuming nothing. Is that a reasonable assumption?
Yeah.
Okay. So the conformal generators, you have plus momenta, which I wrote down at top. So I'll use the usual notation that the d equals 4 vector, I'll write with an undotted and dotted index, like in Western Wagner. So if you don't understand notation, ask very quickly, because otherwise you'll get lost. So this is the translation generator. Now you also have the conformal boost. Oh, the only thing, one thing you can write down, which is actually, sorry, let me call this new. That's the usual thing they call it. So this is the conformal boost. And now, one thing I should tell you is that this is supposed to be the conjugate momentum to this.
So it's the product of what are you doing here?
I'm writing down the conformal generators
In terms
of these twistor variables. Now what I didn't tell you, which I need to tell you, is that this is the conjugate momentum to this, and this is the conjugate momentum to this. So lambda bar A dot is going to be interpreted as d mu A dot. And mu bar A is going to be interpreted as dd lambda A. So of course I can also write this as dd lambda A, dd bar lambda A, but if you want to think of this as a linear operator, then you should think of this as dd mu, and this is like dd lambda bar.
How did you raise the indices in the second equation? Left hand side is downstairs indices.
Oh, sorry. So let's just raise it.
So what is K?
The conformal generator, so the conformal boost. So the conformal group has translations. So probably I should have done the ones that you recognized first. So dilatation is something which scales lambda and mu in opposite directions. So it's going to be lambda A mu bar A plus mu A dot minus. Okay.
And PAA dot, that notation.
That's the momentum.
Yeah.
So, okay, so the notation. So PAA dot is PM sigma M AA dot, but this is the power vector.
So these lambdas are what people usually call the spinor helicity variables, right? So now
Kind
you
of
are
is called
saying that.
twistor variables. Isn't it?
So now you are saying that when you consider it together with mu, that's a twister.
Yeah, so let me say, it's a little bit psychology too. So at some point, twistors was an isolated phenomenon in Oxford. Anybody outside Oxford who used the word twister would be exiled. So these people call it spinor helicity variables, and then it became. But now twistors are popular again, so now you can call them twistors. But so these are the twistors here. Mu is, I mean, okay, you understood what I said.
So mu has lower index, right? So how are you raising?
The raising in lowering is just like Western Bagger with the epsilon A.
I see.
Okay.
And how is mu A defined? Is the star of mu bar A, is it?
So what is the complex conjugate to mu? Is
No,
that-
in the second equation for K A dot, you have mu upstairs A, right? How is mu defined?
Sorry. So raising and lowering indices here is done using the epsilon tensor.
No, but here, in your definition,
You again? I have, oh, sorry.
yeah.
Thank you. Okay, that was a super.
Ah, okay, so, yeah.
Sorry. So you can see that all these generators have one unbarred and one barred. They always have one of these and one of these. Because of course they act linearly. So this is like mu, dd mu, lambda dd lambda. Okay, then of course you also have the Lorentz generator. So this is going to be lambda A,
This is the state transformation.
dilatation. Okay, so you have the Lorentz generator split into a self-dual and anti-self-dual part. So you have lambda A, U bar B. So essentially the only thing you can write down, you don't have to think very hard. So this is symmetrized. So these are the 15 generators of, am I missing something? No, that's right. These are the 15 generators of the conformal group. So these are self-dual and anti-self-dual parts of the Lorentz generators. This is dilatation, translation, and conformal. Now, this is a stupid way to write it. The smart way to write it is just combine this into,
These are all bosonic, I guess.
all boson. So now I'm doing ordinary twistors. So let's combine this into a 4-component object. Let's combine this into a 4-component object. Y. And then these generators are nothing but ZA, YB, okay, minus the trace. Which are just the SU2, generator. So there are 15 of these, just 4 times 4 minus the trace. If you like, if you want to write it in terms of how we transform Z, you could write it.
Is it symmetrization or anti-symmetrization in
Symmetrized.
Symmetric.
Remember that anti-symmetrized, if it has 2 indices, is just proportional to epsilon.
Ah,
So the anti-symmetrized part of the anti-symmetrized is here. But there's another part which is not part of SU22. If you just take the trace of this, you get U22. So the U1 part of this is not part of the conformal. So what the U1 part tells you is the number of Z's minus the number of Y's, because Z carries, you can think of this as a projective object, and Z carries projective weight 1 and Y carries projective weight minus 1. So if you took the object ZA, TDZA, if you like ZA, YA, this is the operator which just counts the projective weight, which is going to be related to helicity. Okay, so, any questions?
I'm sorry, CADCB is what?
This one?
No,
This
that's
one?
that, yeah.
So these 15 generators can all be written in this form.
Okay.
So this is just a compact way of writing these. Now, if you wanted, you could of course write these generators in terms of P's and X's. So how do you do that? So let's define, I don't know if I should try to use both words. Okay, so mu, if you remember from the talk on Wednesday, the way X comes into the game is you define a relation between mu and lambda in this way. So these are the same, these two. Okay, it's not this one. Now in principle you could have mu bar A is equal to X bar A dot. This would be the complex conjugate of this. But now if you restrict X to be real, that gives you a relation between these. So these are both the same X. This implies mu A dot lambda bar A dot minus mu bar A. I should write it. If this is equal to 0. And it's probably plus. So it's plus just because this index is up. So remember that this object here is equal to minus this object here. Okay, so if we define mu and mu bar in this way, then it satisfies this condition. Now you can do the opposite. You can say, suppose somebody gives you mu's and lambdas which satisfy this condition. And you can show that there always exists an x such that this is true. So that means that if somebody gives you y and z, which satisfies this object here is precisely y, a, z, a. So if this is equal to 0, then it means that it defines an x in this way. Okay, now x is only defined up to a shift of this type. Where p is defined here. So that's easy to see just because if you contract lambda a, you get 0.
Are you supposed to think of these as operators?
So we can think of these, it's up to you. You can think of these as independent variables at the classical level, or when you quantize, you can think of them as operators. So at this level, I'm thinking that.
Yeah, I'm just thinking that the x you are written these, so all components should commute with each other, right?
Yeah, so at this level, let's think of it all as classical. So mu and lambda, mu bar and lambda bar are classical variables. Like I was working with x's and p's, for example, just classical variables. And this is just the relation between the values.
Sorry, this why is this minus lambda a mu bar? Yeah.
This here is because, so remember you raise and lower indices using the epsilon. This is epsilon AB, mu bar B, which is equal to minus lambda A, epsilon BA, mu bar B, which is equal to minus lambda B, mu bar B.
So if z y is equal to 0,
Yes?
then in that conformal transformations, the second term is delta AB, ZC, YC is 0, right?
Then this term is 0.
Yeah, but then there are 16 generators, not 16.
Well, if it's 0, one of the generators is 0. So the U1 part of this you're setting to 0.
But it's counting then this 4 into 4, right? 6.
I'm sorry, here there are 15.
Yeah.
And now what I'm doing is, these are these 15. The traceless part of ZY are these.
Right.
So if I set the trace 0,
Oh, really?
then I have this.
And how does one raise or lower capital A's? And
That you can't do. So so these objects, there's no way to raise this index to make it a Y capital A.
but for instance, in that boxed the boxed equation, I mean, for the generators, in terms of ZAs, that should be say upstairs. Upstairs.
Yeah, it is Z upstairs.
Yeah, put the Z up. The Z is always with an upstairs. And Y is always with
In
an
the
downstairs.
leftmost left.
Yeah, that's okay. So the
Six
trace
plus.
part is del ZC with C upstairs.
This should have been. Sorry.
And the second term.
Second upstairs.
Should you put up 1/4? You want this to be traced?
Yes. Okay, so does everybody see that these relations are defined up to a shift of x in this way?
What is the statement?
So I told you that given a mu and lambda, you can find an x. But actually x is not uniquely defined. Because if you shift x by something proportional to p, where p is defined here,
So using that relation lambda.
using the relation that lambda a equals 0, you find that x is only defined up to a shift of this type. So mu and lambda don't define an x, they define a light-like trajectory. So c is just any parameter. So if you find a single x that satisfies this, then you can shift x by a in a light-like direction and it still satisfies. So it determines a trajectory and not a point.
Sorry, why that constraint? Lambda A equals 0?
It's not the constraint, it's epsilon AB, lambda A, lambda B equals 0. Just a property of
Oh, yeah.
epsilon.
So why does it say it's like? I mean, because it's.
Okay, so p squared is 0 because, do you see? Because a dot is lambda bar a dot, so p squared is lambda a bar a dot, a dot. So it's doubly 0, because this is 0 and this is 0. Okay,
So
so
this doesn't contain all the degrees of freedom of a particle. That's what you have said. In terms of mu and lambda, you have only the right-hand trajectories.
So it describes x and p up to a gauge symmetry. So let's write down the superparticle action. Sorry, just the particle. P n x n plus e p squared. So this p squared generates precisely this gauge invariance at x. So, of course, x has 4 degrees of freedom, p has 4 degrees of freedom, but this constraint tells you that only 3 of the degrees of freedom of p are physical, and one of the x's is a gauge. So x0, if you like, is not a physical variable. So in fact, that it brings up the analog of this in the twistor language is double is mu. I'll try to get the signs right. So it's mu. Plus but now you have, instead of p squared constraint, let's call it p tilde. You have the constraint mu bar a plus mu bar a dot. So this is the constraint which replaces p squared equals 0. So this constraint, I can write this in SU2, 2 notation. This is just y bar y a c dot a plus e tilde y a c.
So this makes the U1 into a gauge symmetry.
Yes. So now you can see you have equal number of variables on both sides. You have 4 and 4 with 1 gauge symmetry. Here you have 4 and 4 with 1 gauge symmetry. The gauge symmetries are different, but they both remove 2 degrees of freedom. So I didn't tell you that, but it's clear that these generators are all invariant if you shift z in one direction and y in the other direction. So that's the gauge symmetry generated by this constraint.
By shifting, you mean multiply by exponential of phi and
Right, so multiply z by e to the I phi and y by e to the minus I phi.
But if you don't impose the reality condition on the coordinate,
Yes.
then you don't have that symmetry. Right?
Right.
So if you want to work in complex coordinates, then this scaling symmetry is not there.
Yeah, you do something, okay, so, yes, so don't, if you ask me more questions about this, I won't be able to answer. But yes, people do work in complex space-time, where you don't have this. So, I don't work in it, so I can't answer the question. But yes, there is a whole literature on this that I don't know very well.
He said projective weight 0 is.
I'm sorry?
The theory that you are describing has projective weight 0, that is what.
So that's right. These variables here, you can think of as being projected, in the sense that the scale part of it, you can gauge. So,
Is there any motivation for complex coordinates?
complex x's?
Yeah.
So, yes, so, okay, so. I like to work in, I mean, when people ask me about reality properties, I say, well, let's work in SO2, 2. So, if you work in signature 2, 2, all of these things are real. When you work in SO3, 1, things get more subtle, and I don't make a habit about worrying about reality properties, but if you do, then in fact there is an advantage to complexifying the space-time.
In 4-dimensional color structure you can get. Color geometry you can get in 4-dimensional gravity complex structure.
Yes, so it's related to what you're saying, yeah. So if you want self-dual fields or things like this. So if you're happy to work in signature 2, 2, I think you never have to deal with this, but if you want to work in 3, 1, it is useful. Okay. Okay, so is this okay? People happy? Okay, so if you're all happy with this, the next thing is to do super twistors. Okay, so
So this E tilde constraint,
this is a Lagrange multiplier.
that is not P squared visible, right? That is something.
P squared, no, so P squared is identically 0 in twistor
Right.
space.
So this one, what is possible physically? I mean,
This here,
yeah.
so this tells you that the fields which depend on, constructed out of the twistor variables, should only depend on the projected part of the twistor variable. So just like, this imposes the Klein-Gordon equation that box phi equals 0. This imposes the equation that ZA, DZA, and phi should be equal to 0. Now, in fact, if you're a physicist, you realize immediately this has to be normal ordered. So it turns out that there's a correction you can include, which is a constant here. Although classically, this is what it should satisfy. When you quantize, you have to decide if y is on this side or on this side, and so there's a constant piece you can add. And that turns out to be related to the helicity. So if you write down functions of z, and you require that when you rescale z, phi rescales by a factor, so when z goes to cz, if phi goes to c to the h phi. So that's just saying that z d dz minus h doesn't have mixed power. It's always okay.
But is there any reason for it to be quantized?
I'm sorry?
Is there any reason for it to be quantized?
The Z,
No, H.
why it has to be an integer, you mean?
Yeah.
Yeah, I think you want phi to be a polynomial. You want to allow fractional powers of Z?
Yeah, I'm just wondering, is there something wrong?
Fractional powers of
Of Z.
where?
So that would be square root cuts and things like that. I don't, I've never seen anybody discussing fractional powers.
So where will you get fractional powers of Z?
If you want H to be not integer,
H will be half, right? I mean, whatever, Spinor Formalism.
so that's a convention of,
Well, it's
of what, if I call this helicity, but is it, okay, so I didn't tell you, I shouldn't have called it H, because it's not quite the helicity.
Okay.
It's, let me get it right, so if it's 0, then it's, helicity 1. I think that's right. So, let me call it, give it another letter just because eventually we'll get to helicity. So y equals 0 is helicity 1. Remember, helicity 0, scalar, is y equals minus 2 from the mistake. And y equals minus 1 is helicity half. So now I can figure out, so it's y is equal to h minus 2 over 2, no, 2h minus 2. Okay, so this was the factor of the half column. Okay, I'm going in the opposite direction. No. I think that's right. That's right. So y is related to the helicity. And in fact, what we'll see is that this looks a little bit bizarre. So in Penrose's work, we mostly consider this case. Y equals mine. But what we'll see when we do n equals 4, z equals 4 super A Mills, that actually when we do this for superfields, the correct constant is y equals 0. For n equals 4, d equals 4 super A Mills, there's no normal ordering. So that's one way to see, in some sense, it's more natural than doing the scalars. Okay, so
You are not quite using the Weissenberger convention for contraction.
I'm not using the what?
The Weissenberger convention for contracting dotted and dotted.
When I hear, I'm being sloppy, but if I wasn't being sloppy, I would be using Weissenberger. In what sense? Are you saying that
Because if you write y capital
A down?
Yes, because if you y capital A z capital A index, then it matches with whatever you are written with e tilde upstairs.
Yeah, so
But
I'm
that is
going to
opposite of Weissenberger. That would give a sign because these are commuting objects. So
because I don't have in front of me the correct formulas, let me say that correct. If I did it correctly, I can use Weissenberger, but the thing that I'm sure about is that this should be equal to z ddz. So this is unambiguous. So it scales from both in the same direction. These and it scales these in the opposite direction.
So this scaling that you are requiring is because you want to maintain those generators.
I want to maintain
This generator. If you write this generator, then it is stressless.
Yeah, so these generators are elements of SU2, 2. So the constraint is the U1 part. This was U2, 2, it would be different. Okay, so that's bosonic twistors. And now I want to do the super twistors.
Sorry, CH or CY in your information? Y.
Yes. so I didn't construct these. I didn't prepare the construction of this. If people want, I can try to say why you have this relation. But let me keep going unless somebody wants me to do that. It's going to take. Okay, let me keep going. So let's do the super case. Okay, so now we want to have, instead of SU2, 2, we want to have PSU2. So this P means that the bosonic parts are just SU2, 2 times SU4. So this is a superconformal group. So of course it has SU2, 2 in it, but it also has some, if you like, internal degrees of freedom. So the variables we're going to use, so we have the same variables as before, mu a dot, a, but now we're going to introduce 4 scalars. So let me use the letter J ahead. And in fact, in general, you could consider n. So Ferber didn't consider n equals 4, he just said general n. And in this case, j equals 1 to n. If you want to do n equals 1, superconformal, super A mills, you just have one of these. If you want to do n equals 4, you have 4.
And something will go wrong if you try to take this to more than 4?
No, at least until you quantize, no. What you would find, of course, is that what you will see is that the helicity gets bigger and bigger as you have more and more a's. So if you want to stop at spin 1, then you have to have n equals 1. Now, okay, and then of course we have the complex conjugate. Let me call it eta bar complex conjugate to A, and it has a down index. So if this is a fundamental of SUN, this is anti-fundamental. And here you have eta bar A, and eta bar. So this now we'll call C. But let me call it, instead of calling it A, let's call it ZR, just to remember that it has both bosonic and fermionic. So R can either be A dot, or J. I'm going to call this small j.
Can one get this like, I cannot have a more than 3/2 spin because these are all massless. Some proof from here.
You asked me why I can't consider any.
That should be, if one can have a proof in this.
Yes, I think so. So you want a superconformal representation, and if you have spin bigger than 1, I don't know any superconformal representation. You can do a free case probably. So if you're just describing free higher spin, then you can have n be as big as you want. But as soon as you have interactions, I think nobody knows how to have interactions of spin 3/2 or spin 2 or higher with preserving conformity. But for the free case, I think it's okay. Okay, so of course the action now is just going to be the same as before, but now we have right here. And now what I claim is this is supposed to be equal. So here, of course, you're going to have down. So you add the fermionic part here, and the claim is that this describes now the super part. The one which we had so much difficulty quantizing. Okay, so let me say why the claim is that these two are the same.
So which two are the same?
Question?
Which two are the same?
The superparticle action that I described in the first lecture, and this action. So I could have already done this for the particle, I mean for the bosonic case. So these generators here I can of course also write in terms of x and p. So what are the generators? So of course the translation is just p. The conformal boosts in terms of x and p, something like p dot x. X dot minus x dot x. The dilatation is just p dot x. And of course, Lorentz generators are Pm, Xm, antisymmetry, sigma Mn. And so we can of course write these generators in terms of the p's and x's. And it's an exercise to show that if you plug in the definition for mu above, and the definition for p here, these generators map to these. Okay, but now we can do the supersymmetric case.
Can I, these, even in the earlier case, these two actions are same because of symmetries, or they are same classically? There is no proof that quantum mechanically they are equivalent?
That's right. So they're the same classically. So if you impose the constraint p squared equals 0, then on that constraint, on that constrained surface, there's a one-to-one map between the p's and x's and the y's and z's on this constraint surface. Okay, so classically they're the same. But you're right, when you quantize, you don't have a proof that they're the same. And in fact, they're different because, as I mentioned already, if you quantize the particle, you get box phi equals 0, right? Describes a massless scalar. Nobody claims when you quantize, so let's just do the ordinary, not the super case. There's no way to get the spin 1 out of quantizing the particle, massless particle. But when we quantize this, as I told you, depending on the value of y that you decide to use for the normal ordering, you can either get the massless scalar, you can get massless spin 1, you can get massless spin 1/2. So you can in fact get any helicity. So in that sense, they're not the same at the quantum level. Okay, so now we're going to do the super case.
This Lorentz, this generator written in this form, do they have this asymmetry of x into x plus cp? They don't. Because this x dot x term will have some x dot p.
Let's try. This one is invariant. So
Yeah.
suppose we're on the surface with
This is invariant because p square is 0. But it's x dot x.
Let's try. I haven't thought about it. So this one will go to p dot x, a delta k. So this term won't change. This one will. So you'll get p dot x, cp a dot. Now this one will transform. This will go to minus c p dot x times d a bar.
Into 2.
Oh, 2. Okay, so that's a half. Sorry.
Oh.
So a small thing, it's a commutator between P, M and N, right? M and P.
This one?
Yeah.
Yeah, I meant. I think. Okay, so yes, it is. Okay, so one can of course generalize this to the superparticle case. These are just the Noether currents coming from the symmetries of the action. So I'm not going to compute them out here. But one thing I have to tell you is what's the relation between, I told you what the relation is between mu and x. But what about theta? So if you want to translate, so this is going to have theta dependence, right? So doing I want to claim that these get mapped to just now ZR YS minus, I guess 1/8 delta RS. In fact, probably, okay. So this is, here let's count the number of generators we have. So R goes from 1 to 8 now. This goes from 1 to 8. And I did this wrong. No, I'm being too sloppy, sorry. Because I have to subtract off not just the trace, but the trace independently in these two sectors. So this object here has 32 fermionic symmetries and has 30 bosonic. So the bosonic, of course, are SU2.2 times SU4. The SU4 are just symmetries that leave the mu and lambda invariant and just rotate eta in the usual R symmetry, right? And the 32 fermionic, 16 will be space-time supersymmetries. So this n equals 4, z equals 4. And the other 16 will be superconformal. So they won't be the usual supersymmetries. They will be ones which, in some sense, when you commute them with the usual supersymmetries, generate Lorentz rotation. Okay, so this algebra probably people know from ADS5 times S5. So of course all of these generators are just act linearly on these. Right? It just transforms like a PSU224 vector. So let's write down some of the symmetries. So for example, what are the supersymmetries? Supersymmetries are very simple. They take, for example, QA.
So the two symmetries that you are going to remove are just
The two bosonic symmetries?
yeah. So the phase of the bosons and the phase of the formulas, is that
Yes. So the U1 part, so if you scale all the etas by the same amount, that one you're taking away. And if you scale mu and lambda by the same amount, that one you're taking away. Okay, so what are the supersymmetries? Well, just by staring at this, there's only one thing you can write down. Well, there are two things. The thing. The only other thing you can write down with an A and a J index is mu bar A, eta S bar naught. So these are the things you can write down with an A and a J. So let me remind you what the superconformal generators are. You have QAJ, Q bar, A dot J. You have SAJ and S bar, A dot J. So there are 8 of these, 8 of these, 8 of these, 8 of these. And those are the 32 generators. And now I'm telling you what they are in terms of these. Essentially, only one thing to write down. So let's just see that they generate the right algebra. So Q with Q bar is of course supposed to give you P. Well, that's trivial because the only thing which doesn't commute here is the eta and eta bar. And you just anti-commute those and you just get lambda A, lambda bar A dot, delta JK. Similarly, S with S bar, if you commute, again, eta and eta bar won't commute, it's just going to give you mu mu bar, which is just the conformal generator. And then you have the mixed ones, Q with S bar will commute, because it's eta bar with eta bar will commute, and it's lambda with mu which commute. But Q with S won't commute, it won't anti-commute. So it'll give you a term coming from the commutator of this, and a term coming from the anti-commutator of this, which is just going to generate the Lorentz and dilatations. Okay, so that's the usual superconformal algebra.
Interval will anti-commutator will be 0.
I'm sorry?
You said that QAJ will be S bar A dot.
This is 0, this with this. Okay. Of course, the other bosonic generators that I didn't write down here are the R symmetry generators. So you have R, JK. This is just eta, J, eta bar. So these are all the bosonic generators, and these are the fermionic ones. So I didn't tell you yet what the relation is between the etas and the thetas. So if you want to show that these generators here are the same as these, I have to tell you the relation between them. So the relation between P is, I already told you, P A dot is lambda A lambda dot. It turns out this relation for mu has to be modified. Well, let me tell you what eta is first, and then I'll tell you about it. So eta j is going to equal to lambda a theta aj. So when we're doing the in 10 dimensions, this would be the action. Okay, where these are 10-dimensional spinor. If we dimensionally reduce to 4 dimensions, these become a carry of j there. So j is 1 to 4. And the action becomes now collinear. This is the action in 4 dimensions. Theta and theta bar are the usual Westbagger 4-dimensional spinors. And if I'm doing n equals 4, then there are 4 of them. So the relation between eta and thetas will be of this type. So you use lambda in in order to contract the spinor index of the theta. Of course, eta bar is the complex conjugate. And the mu gets an additional term. Mu, instead of being just this, it has a fermionic contribution too. So mu A dot from theta E dot J into J. So this you don't see in the bosonic case, but you need to add this. There's an easy way to see it. I'll tell you in a second why you need to add it. Now, using these relations, you can show that the superconformal generators coming from this action are equal to the superconformal generators coming from this. Okay, to show that this is what you want, the only thing you have to show is that with this definition, yz equals 0. Okay? Remember before we used this relation of mu and x in order to show that mu lambda bar plus lambda mu bar is equal 0. When you do this, when you take mu lambda bar, so this equation here implies A dot, lambda bar A dot. So that will give you put a lambda bar here and a lambda bar here. If you subtract mu A, lambda bar A dot, yes. So for the bosonic case, if you just did this, you would get 0. In this case, you don't get 0 because you get a term left over here. But that term left over, when you contract this with lambda bar, you just get eta bar. So when you, in order to get 0, you have to also add the term eta bar j, eta j. So this now is 0. And that's what you want. You wanted the full y and z. Okay, so this is four-dimensional super twistors. And now the last thing I want to do is say what the wave function looks like.
So there is still one constant, is that what you are saying?
I'm sorry?
There is still one constant within all the variables.
This constraint here.
Yeah.
So, and there's also a gauge invariance, which is if you scale all of these variables in one direction and all of these in the other direction, the wave function should stay invariant.
I'm just wondering, the number of conformal generators is 2 less than the number of things you could write down, right? So why hasn't a new constant done that?
So what is it?
Because you reduced,
What is the question?
the number of generators got reduced by 2, right?
Where?
Because separate scaling of the bosons and fermions are removed.
Right.
So one would expect that there should be 2 independent constraints on the variables.
Eta there was one more separate scaling metric.
Yeah.
There is an overall scaling of that entire column vector versus opposite scaling of the other column vector. That is one unit.
Yeah.
But etas and eta bars could scale without mu's and lambda scaling.
So could that
That's what it's saying.
That would reduce that rjk from 16 generators to 15.
yeah, but should it give a constant? I mean, to be
Maybe both of them are not separately placed like that. So you want it.
Let me think about it. I understand your question. By the end of my lecture, I'll try to have the answer. I don't have it right now. So what you're asking is if there should be another constraint which generates.
looks like, yeah.
Yeah, let me think about Okay, so let's now try to construct a wave function built out of these y's and z's. So you have four of these. So let's obviously we have the wave function either be a function of the coordinates or the momentum, but not both. So let's define it to be a function of the coordinates, these. So there are four of these eta, so you have 2 to the 4 terms. So let's just write out what we call these terms. So we have 8 bosons and 8 fermions. So assuming that phi is bosonic, the lowest component is bosonic. Here you have 6 bosons, and here you have the last boson. Now if phi has projective weight 0, so if
This symbol is with epsilon cancel, is it? Contract.
these 3's are, that's right. So when I write the index down, it's because I contracted these 3 with an epsilon. Epsilon with 4 indices. And we're going to choose y to be 0. So that means this object here should be a function of mu and lambda of degree 0, which means if you rescale mu and lambda by the same amount, this object should not rescale. So it says projective weight 0. Now eta has projective weight 1. So if this should have projective weight 0, then chi should have projective weight minus 1. And this should have projective weight minus 2, minus 3, minus 1. If I did the computation right before, I'm not sure I did. I erased that. But, this is spin 1, this is spin minus 1, or helicity 1, helicity minus 1, this is helicity 0, and this is helicity plus half and minus half. So these are the 6 scalars, these are the clockwise and counterclockwise gluon, and these are the gluine. And they only appear in the physical components. So, of course, a gluino or a gluon would have 4 components, but only 2 components appear through the superfill. So this would be the self-dual, and this would be the anti-self-dual. Okay, so what was shown by Witten was how to compute scattering amplitudes using this construction. So that's okay. This up to now, this was all known by Ferber, 1976. Okay, any questions? Okay, so there's one question I still have to answer. I'll think about maybe during the break. But
so this thing about this separate gauging is what supersymmetry and supercontrol transformation is rotated. When you are breaking into one.
I didn't understand the question.
So there was this issue that this mu lambda and this eta could have different Q1s, right? So should there be 2 constraints?
That's what he was asking. I said I will think about it during the break. If you know the answer.
So I'm just saying, shouldn't supercontrol, so shouldn't supersymmetry rotate one into each other? So this.
Yes. So
then
these.
why should one impose separate gauging for both? So that will rotate them into each other, right? In the full PSU 2.
Yeah. So you're saying you're not.
Why should they have separate gauging? Because Q's and S's rotate them, right? What is the asymmetry in one will be space-time? Because Q actually rotates.
Yeah. So there's only one projective.
Right, there shouldn't be one.
Right. But then his point was, well.
Because it's a full supersymmetry, you don't have to separate.
I think his point was that. So I remove one of the. So if I just write down YAZA, Naively, this has 31 bosonic components, and not 32.
There is this overall phase of all super generators. You can include, right? I mean, all of them are having the same phase. This is the U1 part of the. I mean,
That's what we removed last time. Boson last time we removed.
Can I suggest?
SU4 you could have SU4, right? Why should you remove?
Let's do
The
this in
answer
a break.
is fine.
I'm sure there's a simple answer, but it may take us 10 or 15 minutes to get there. So I think during the break, so we can take the break now if you want. I don't know. You guys probably want tea. That's the problem.
So he comes at what time? Probably 11:30.
Okay, so let me say now about Witten's action. And so I can't do this either, but if you can just separate out that question from the rest of your.
Another thing like say n equals 2 superconformal field theory, this comes out just.
I'm sorry?
If you have n equals 2 superconformal theories.
For n equals 2, then you would have to put in. Okay, so the nice thing about n equals 4 is that there's unique multiplets, which makes sense. With n equals 2, you could get a scalar multiplet, or you could get a vector multiplet. So those would depend on the choice of y that you put here. And similarly for n equals 1, you can get multiplets. So for example, there's an n equals 1 multiplet with a scalar and a spinor. There's one with a spin 1 half and spin 1. So depending on the choice of y, you will get different, what's it called, super spins or some, you'll get different multiples. The same in n equals 2. But of course, in n equals 4, this is the only superconformal multiplet you can write down. So in some sense, it's special in the sense that there's no...
You can have different etas like eta 1, eta 2 and some theta 1, theta 2. Instead of SU4,
Yes.
you can have SU2 plus SU.
Yes. So you could do SU2.
N equal to 2.
Yes, you could do n equals 2. That's right. So this n is at this point is arbitrary.
Yeah.
But if you want to do an interacting theory, I think in n equals 4, d equals 4, you're stuck with this multiplet. There's nothing else you can do with conformal. No, you can do n equals 4, d equals 4 supergravity conformal also. So, okay, that's done in it. Okay, let me say something which you could have put an index on this. So if I put an index on this, I can change the Lorentz properties if this index transforms under the Lorentz transformation. So if you want to do conformal supergravity, n equals 4, you put an index on this. Okay, I don't. If it's a scalar, I think the only thing that can make sense out of it is the n equals 4, d equals 4.
But I was asking, say for example, n equals 2, for it to theoretically superconformal, there's a relation between the number of flavors and number of colors. Does it follow from?
I don't think so. So at the quantum level, you're saying?
Yeah, I mean, because when you write them
To the beta function.
Yeah, so exactly. I mean, does it follow from?
I don't think at the quantum level this says anything useful. So at the classical level, it tells you what you can write down, but at the quantum level, I think you have to do some work. Okay, so let me just say what Witten's action. Well, actually, this is not Witten's action. Witten did something a little bit differently, but I wrote the paper soon after in which I wrote the action in this form.
Sorry,
Yes.
if I want to quantize the action, how can I do that?
This one?
Yeah.
So you define Poisson brackets and you find yr zs. So it's either commutator or anti-commutator depending if these are fermionic or boson. This is equal to IH bar. So, alright. You're finished.
Just,
Yeah, because this is a first class constraint.
oh, I see.
So there's nothing else to do. So of course the problem with doing that for the superparticle is that the canonical conjugate to theta is not an independent variable. Here the canonical conjugate to z is just y, so there's nothing else to do. Okay, so So the action for the string is actually almost as stupid as you can do, but it turns out that there are generalizations of this stupidity which makes it interesting. So all you do is do this. You see, that's a string theory. So all you do is you change the time derivative of the world line to an anti-homomorphic derivative. So now it's a worldsheet conformally invariant. So it's a little bit funny you have a constraint, but that's not
These are
so.
only right movers.
What's that?
These are only right movers.
There are only right movers, so it's so stupid you don't even put in the left one. You could have put them in, but then nobody knows what to do with them, so don't put them
But
in.
it's string theory, what kind of string theory? Do you give type 2?
It will give a theory of superyang mills and conformal supergravity.
I see.
So it's not the usual superstring. But actually what we'll see maybe after the break is there's another version of this where instead of y's and z's use x's, and then you get the alpha prime equals 0 limit of the superstring. So and
But
this,
that was already there in the particle action, right?
this is essentially the particle action. I
Yeah.
mean, you're trying to describe n equals 4 superang mills, so it's just a massless theory, so there's no reason you need to have sigma dependence.
Right.
But when you want to do interactions with particle theories, it's complicated because you have to say what a vertex is. In string theory, the nice thing is, you don't have to do any work to do interactions. You just say, okay, I have some curved world sheet, and that's it. Now I have interactions. So how this works is something that's not yet, well, it's not understood by me, but the fact that it gives the right answer, it does. Trivial. So,
So is the unit comment that
Yes, sir.
if I want to introduce left movers, there will be problems for it?
well, you can introduce them, but you don't know what to do with them. So you'll get an extra set of twistors.
Or
You see, we already have superang mills. You might think, okay, that'll give me supergravity. But when you double the number of twistors, it's not like, let me remind you, you don't normally double the number of x's. Right? You just double the number of thetas. But since the y's and z's contain the x's, if you double these, you get twice the number of x's. So that you wouldn't be getting what you want.
But X has left and right mover.
Yeah, you would be getting something. Nobody has made any sense out of what that is.
So yeah, if I just wrote it as half y del bar z plus half y del z.
The same y or a different? You want to put a y left?
No, same one.
The same y. You want to add this plus? You want to do this?
Put a factor of half.
That's not conformally invariant. So you want, on your worldsheet conformal transformation, z is going to have conform weight 0, and this will have conform weight 1, 0.
But this is del root.
So yeah, this is 1, 0, and this is 0, 1. In order for this to be conformally invariant. If you added this term, then this would no longer be conformally invariant. So you could put in a different one.
Yeah. Or you could use the same z but different line.
That probably screws up the quantization. So if you have the same z and different y's, then the equation of motion for y is that you get both d bar z equals 0 and dz equals 0. So that kills, that's it, it's constant, that's not really long.
So, like in the pure spinor case for the previous cases that you were doing, there was this constant lambda a, gamma n, lambda was 0.
Yes.
So does that constant have any analog here?
Yeah, so what you just told me is the pure spinor constraint in 10 dimensions. In 4 dimensions, the analogous constraint is that lambda here, if you take sigma m, this is obviously 0 because these are the spinors of the same chirality. So it tells you that the pure spinor constraint in 4 dimensions just tells you that this lambda variable doesn't have any A dot component. It's a vile spin.
But for this, if I take the instead of superparticle, the only particle sample, which also has a twisted expression, right? Twisted action for the particle, not superparticle.
Oh, yes, so if I just drop the fermions.
Yeah.
Yes?
So this is fermionic.
This doesn't seem to work if you drop the fermions.
Okay.
So we'll see later, but if you want to compute amplitude, so of course, you can write this down for any capital N, calligraphic N. You could consider N equals 0, but nobody has been able to compute interactions using twistors except for N equals 4, D equals 4.
But in string theory, if there is a string theory, then we should be able to do it. No? We know that prescription.
Well, we can say there is this conformal anomaly, so it's not obvious that you can just drop the fermions and the theory is still consistent.
So this one doesn't have any conformal.
Okay, if I do things carefully, it won't. So let me do things carefully and we'll see that.
But for the bosonic case, conformal anomaly will be the Einstein equation.
No, it's in a flat background.
It's in the worship conformal.
So there aren't 26 x's, there's only 4 of them, right? So,
Okay, I see.
okay,
Oh,
so,
I see.
okay, so,
Central term.
yeah, so I mean, because we're looking at pre-amplitudes, having the wrong central charge is not a big deal. You can do tree amplitudes in bosonic string theory in any dimension you like. You don't get.
Is it?
No, is it correct? You can certainly do Yang-Mills in any dimension you like, tree amplitudes, and nobody complains. Maybe for the massive states, you might get states of the wrong norm or something like that.
Formulation of the whole thing, the scattering amplitude probably needs.
Okay, I probably said too quickly, but certainly you can do the massless states of the string tree amplitude, I think, in any dimension. So certainly what Carlos was saying, you can generalize to any dimension you like.
But when we calculate this correlation function, the general form that require immense conformalism, right? So
No. And the quantum,
Independent of what is already
let's see.
in a tree level.
that form requires conformalism.
Three-point functions,
Correlation function.
and the sphere would be independent of.
Just matches with field feedback.
The point is they don't play any role. I mean, you just use the extra excess to cancel the conformal anomaly.
Yes, but they don't enter into the
Yeah.
amplitude, so that you can just, it doesn't matter what your starting point was.
Yeah.
So I will tell you how to get rid of the conformal anomaly, but nobody understands.
But
Yeah?
similar technique, similar argument can be used without fermions here.
No. Okay, so let me, so that, I don't know how to get rid of the fermions here and compute the amplitudes. Nobody, I don't think anybody does. I didn't tell you how the fermions enter here, but you'll see in a second when we compute an amplitude.
But you had the construction of y and z earlier.
Yeah, so the y's and z's are here.
No, in the bosonic case.
Yeah, you can write down this action for pure boson, but writing down the action is not enough to tell me how to compute Yang-Mills amplitudes. So, I mean, it's certainly not clear how to use this action to generate Yang-Mills amplitude.
No, but you think from the NSR n equal to 2 you can come down to redefinition. I think you have done it.
Say it again.
NSR variable you can redefine, start from n equal to 2, then you can reach this action in conformal ways.
No, I don't think so. I don't think you can get this from NSR. I think, in some sense, this is its own starting point. I don't know how to connect. One of the open questions is how to connect this with any of the other string theories. Before Witten's paper, I don't think anybody had an idea how to do something useful with this. Okay, so Well, let me get there, and then there'll be more questions after, but let me just say about the conformal anomaly. So, to quantize this, first of all, I did tell you what the BC ghosts are. So, if you couple this to a curved Wilchit, you also have ED bar C. And in fact, you also need, that has C equals 26, and C equals minus 26. And you also have to gauge fix E tilde, so that generates a U1 gauge field, which generates its own ghosts. So the BRST operator is going to be C times Y TZ. So this is the stress, this is the normal stress tensor. And then of course you get the usual BC. But now you're also going to get a ghost for this. Let's call it C tilde times YZ. And this is going to be a ghost of conformal weight 0. So that means when you write it in the stress tensor, it contributes C equals the fermionic, so it contributes C equals minus 2. So this gives you C equals minus 2. This gives you C equals minus 26. And this gives you C equals 0. Because you have an equal number of bosons and fermions in Z. So in order for this to be...
there is no C tilde, B tilde, C tilde, huh?
No, so this is an abelian U1. And the other thing you need to check is that this has no U1 anomaly. But it doesn't because you have an equal number of bosons and fermions. So this would be the first place you would get stuck if you were doing with fewer numbers of fermions. So YZ would have a U1 anomaly. So that's, in some sense, that's the justification why you're stuck with n equals 4, d equals 4. Okay, but then to get a zero conformal anomaly, you have to add another sector, which I'll call T. Okay. So in fact, you have to add another term to the action, which is a current algebra of C equals 28. So at C equals 28, just to cancel this C equals minus 2 and C equals minus 1. Now what do you do with this current algebra? Well, this is Yang-Mills theory, but I can tell you what the gauge group is. So the gauge
What was the counting again? You got C equal to...
So this contributes minus 26.
Okay.
This, when you quantize this, contributes C equals minus 2 because it's fermionic and conformal weight 0. And the matter field Y and Z contribute C equals 0 because you have an equal number of bosons and fermions. You have 4 bosons and 4 fermions. So you need a C equals 28 sector in order to cancel the conformal anomaly. And in fact, you need an additional sector if you want to get some non-abelian gauge group. And to get something non-trivial, you have to introduce this sector n. Now, why C equals 28? When we started writing these papers, we thought maybe it had something to do with some magical modular invariance, like heterotic E8 plus E8. But since we never could compute a one-loop amplitude, we essentially gave up in trying to explain this. But it might have something to do with modular invariance in one loop.
So modular invariance, why hasn't it been checked?
Nobody has been able to do a one-loop amplitude. So
What's the prescription? That there is no prescription to do it?
I didn't tell you what the tree amplitude prescription is yet, but I can't say people haven't tried, but in all of these massless theories which don't have any alpha prime, so also these infinite tension limits, it's not obvious that it makes sense at the one-loop level. So I shouldn't say that people should stop trying, but it's just not obvious to me that they're going to get anywhere. But that's not my point. My point is just to introduce these twistors. So I should say a little bit what the motivation is. So the motivation is to try to understand the 10-dimensional theory using twistors, in the hope that some of the simplifications that come in from the 4-dimensional theory get translated to the 10-dimensional theory. And maybe even will help with ABS 5 times S5. Sometimes it goes back to the 4-dimensional theory. So I'm not really that interested in making sense out of these theories. I'm just trying to get some intuition about the 10-dimensional. Okay, so we have these fields, phi, which I just erased. And one can ask how to compute scattering amplitude. So this is obviously going to be related to the vertex operator. Okay. But somebody has to tell you how to do the path integral over the z. Okay, so for a tree amplitude, you're going to have to integrate over the dz. And you have a certain number of vertex operators. Now, this is a projective space, so you can make sense out of this kind of integral. But okay, you have to know how these v's depend on the z's. So essentially, the way to figure out how these phi's depend on the twistor variables is to first write them in terms of the x variable. So this is going to be something like this thing. You want to write something like e to the ik dot x. So you want to choose them in some basis such that the momentum is a diagonal operator, so then you can just compare with the usual Yang-Mills operator. Okay, so what is e to the ik dot x? Well, p is the operator lambda bar. So the way you write down the vertex operator is you fix lambda. So lambda is a function of z. And let's say it's equal to lambda r. So this is the vertex operator for the rth state. So p is going to be equal to lambda r, lambda bar r. Okay, this is the momentum kr. A dot, lambda r, so this object will have eigenvalue lambda r when lambda hits it. And now you're going to add a term e to the I mu lambda r dot mu. So this object has the property that when you hit it with lambda bar, when the lambda bar is like lambda bar is the conjugate to mu. So if I Fourier transform this object back into lambda bar space, this is just going to give me delta of lambda bar minus lambda bar. Okay, so this operator here is going to reproduce.
So lambda bar we don't talk here is just a number, I guess.
That's right. So this is the external momentum.
You could in principle choose the lambda and lambda bar a dot as coordinates, right? Then
yes. And this mu is of course a function of z. Okay, and then of course you just multiply this times these functions of 8. So these are the vertex operators we're going to use. And now you can see that lambda of z doesn't have any poles. The vertex operators don't depend on mu bar. Which means that lambda is just going to be a holomorphic function. There's no sources for lambda. So naively we would say that lambda is just a constant. So it's just a constant, let's call it C. Now that obviously is not going to work, because if you have vertex subspace with different values of lambda r, you won't find any solutions to this equation. So the trick is to consider U1 fields here, which are not non-trivial. So by considering U1 fields which are non-trivial, you can shift the conformal weight of Z from being something which has to vanish at infinity to something which is allowed to have polynomial dependence at infinity. So if this was a conformal weight 0 object, then the conditions at infinity would force it to have only these 0 modes. It would not have any more 0 modes. But if this had conformal weight -1 instead of being conformal weight 0, then there's another term you can add. Instead of going to 0 at infinity, it can blow up like Z at infinity. And if you have -2, okay, then you can have Z squared. Now, once you allow this type of behavior, now you can find solutions to this equation. And in fact, the amount of twisting you do here is related to the fact that you're going to compute an amplitude which is called an MHV amplitude. So maybe all of you have heard of this, that in Yang-Mills theory, of doing an endpoint scattering, you can consider, let's just do gluons. You can consider all the gluons being of the same polarization. That turns out to vanish. If you consider amplitudes where one of the gluons has the opposite polarization, it still vanishes. The first one, which does not vanish, is one with two of the opposite polarization. So this is called MHV. You can consider near MHV, which would be 3, etc. Now it turns out that when you compute these amplitudes, to get the non-vanishing answer, the degree that you choose for lambda is related to the fact to which helicity amplitude you're computing. So let me try to say in a few words why, and then I'll stop. So depending on how much detail, I can go into detail on this, but obviously I can't go into detail on everything. MHV.
But so you are saying that depending on what amplitude you want to calculate, you assign different background charges to lambda?
Yeah. So
it's not the same strength curve which gives the amplitudes arbitrary for that.
Right. So the point is, well, if you have a U1 gauge field, you're supposed to integrate over all possible configurations of the U1 gauge field. So you can have different instanton numbers for that U1 gauge field, and you're supposed to integrate over all of them. So you have a sum, that turns into a sum from minus infinity to infinity of the different computations. So this would be a computation with gauge field with instanton number n. But what will turn out is that at a fixed instanton number, only certain amplitudes will contribute. So let me try to explain why, just in a word.
So that is where in the path integral?
That's right. This is so when you do the pre-amplitude path integral, you have an integral over z. So normally on a disk, you say there's no moduli to integrate over, because all disks are conformally equivalent. But if you have a U1 gauge field, they're not all equivalent, because different instanton numbers are topologically equivalent. So in fact, it's not sufficient to just integrate over Z, you also have to sum over all the different instanton numbers. And the different instanton numbers are going to modify the degree of lambda in a way that they'll just say why the changing lambda is related to these helicities. So, of course, if I change the degree of lambda, I also have to change the degree of all of the z's, including the etas. So, this integral here, for the etas, gives me an integral over all the etas. So if eta is degree 0, then it just has one 0 more. And this would be just, there are 4 etas, so it's just the 4. But if you have different degree, this is going to get more and more 0 more, just like the lambda has more and more 0. So in fact, this is going to be 4d. Or 4n. Well, I'm not being careful with my letters here, but as you change the degree, you'll get more and more etas. And that's going to be related to these different helicities. So let me explain that here. So if you look at the expansion, you see that A plus doesn't come with any etas, whereas A minus comes with 4 etas. So if you want to change the number of A pluses relative to A minuses, you have to also change the number of etas that appear in the expression. So that's why these changing the degree of lambda is related to changing the helicity that appears in the amplitude. Okay, so that's the general idea. The idea is that in order to get the Yang-Mills amplitudes, you have to integrate over the lambdas. You have to allow different degrees. And there's one more point that I should make
And the
is that,
central charge doesn't get affected by all this?
I'm sorry?
The central charge. Earlier you have done the central charge calculation, right?
Right. No, the central charge is, it gets a contribution of -2 from, okay, good. So you're asking if when you twist,
Yeah.
if the conformal anomaly changes. So it doesn't, because this has no U1 anomaly. So adding dyz, so if you have a stress tensor and you add dj, where J is the U1 current, then in general this will change the central charge of the stress tensor. But the change in the central charge is proportional to J with J. And since this is 0, there's no change to the central. So once again, this is only true for n equals 4, d equals 4.
So this is 0 just by cancellation from both arms and bottom arms.
Yeah. Okay, so there's one more important feature which is unusual, which will come back to us later, which is that fixing lambda z equal to lambda bar, given this kind of function of lambda, is going to fix z. So if you know the lambda r's, and you know the c's, that fixes z for you. So the locations of these vertex operators is fixed on the surface. And that's going to be related to the scattering equation, go to 10 minutes. So it's an unusual string theory in 2 ways. One way is that it just involves holomorphic fields. And the other thing is that in effect, you don't integrate the vertex operators over the Will chain. You just fix them at the locations such that the vertex operators have the right twistor properties. So these two things somehow fit together to give the super Yang-Mills amplitude. So the formulas are not so simple to work with. So what you have to do is you have to solve these delta functions to find where they sit. So for 4-point scattering, or you can do it easily. Okay? For MHV amplitudes, you can do it easily. As soon as you go to the next MHV, it gets to be a horrible mess. So for 4-point, the only thing you have is MHV. For 5-point, the only thing you have is MHV. Because 5-point, obviously, you either have 2 minuses and 3 pluses, or 2 pluses and 3 minuses. For 6-point, you have 3 minuses and 3 pluses. And it was a conjecture for a long time that this 6-point amplitude reproduced this. And I think it was only proven recently. Well, it was proven first by numerical computation. I mean, it was shown to be almost what you wanted by numerical computation. And I guess now it's known that it's correct to all orders, right? Do you know this kind of? I think now people who have worked on the scattering equation now have been able to prove that it's...
Yeah, but it's a different formalism.
No, but to show that this reproduces the Feynman diagram computation.
In your setup?
No. I'm saying, so this is not, the answer, okay, so I should be clear. The answer here was first written down by Witten computed using his string, and then Roybon and, what's her name? From Brown. Sorry? Yes. They wrote it in a form that's related to this. And Volvich was the one who checked the 6-point. Maybe it took her a year to check it. But since then, so they conjectured that this, of course, reproduced the known answer using Feynman diagram computation. But since then, I think it's been proven that these are the angles amplitude. But in any case, okay, it's not. I think it's now proven that this gives the right answer. But the way you get it is just so unusual.
All this progress regarding some into the K, MHV, amplitudes.
That's right.
This is not using this formalism.
So, what people have done is they haven't. Nobody uses the string theory to compute anymore. But they use this formula, which originally came from the string theory, and generalized it, to even loop amplitudes, etc. But for the loop amplitude, nobody knows how to get it from the string.
But even for higher point tree level,
Yes.
this is not the starting point.
For higher point tree, yes. So this has all the higher point trees.
But you are saying that problems with checking that this reproduces Feynman diagram calculation.
Yeah. So the expressions you get don't look anything like Feynman diagram computations, because first of all, they're all implicit because you have to solve these delta functions, and nobody knows how to explicitly solve these delta function equations, except for special cases. So getting explicit numbers out of this is not so straightforward.
So that's what I was thinking. So all this n to the k, MHV, this various tree level amplitudes, what do they use to do the calculation? They don't use this directly, right?
You have to ask somebody else. I don't know. So these ideas have just gone through transformations by Nima, by Freddy, by other groups that, it's, okay, so I don't know. Okay, but that's essentially, okay, so let me think about that question. And I guess the next thing I want to do is say what the 10-dimensional, there's a 10-dimensional analog of this. And I'll say a few words of that.
Try to come back in 20 minutes.
So the additional generators that I should want were these generators here. So A to J, A to bar J. If you like this thing plus, you have this one, and then you have the one with. So these two are related by this constraint here. But then you could ask for the difference instead of the sum. So classically, Ashok is right. Classically, the difference is fine. It's also a symmetry of this theory. But when you quantize, although yz with yz has no anomaly, this goes like 0. So this is regular, but if you take this with this object, now it has a singularity, so this has a double pole, so there's 1 over 1 minus z squared. So although the symmetry generated by this is fine at the classical level, I think there's an anomaly when you include this twisting. So that's easy to see from these Bn imagery. So if this were symmetry of the theory, we'd say that the amplitude would always have to have an equal number of etas and eta bars. But that's clearly broken. So the amplitudes that contribute have either 4 etas or 8 etas, etc. And that's because this generator doesn't commute with this. Is that okay?
So we didn't see it in the bosonic case because we didn't go as far as quantizing it and getting similar thing to have happened there also.
Yeah, in the bosonic case we didn't, I mean even this by itself is anomalous in the bosonic case.
Yeah.
So we wouldn't have even been able to twist in the bosonic case. So these two bosonic symmetries, okay, so when you do PSU 224, is the P, which is the scaling one we're talking about, and there's the S one. And so now that's the one. This is bonus symmetry that is broken.
So at the level of superparticle, you could have imposed.
For the free particle, this is fine. So free super Yang-Mills has this bonus symmetry. But as soon as you do interaction, it's broken. Let me see if there's a clever way to see that. Yeah, you can see that from the Yang-Mills action. So the Yang-Mills action, you have the term FMN, FMN. And plus you have the term chi E slash. So this is A dot A. But then you have terms like phi jk, so here's a j, and you have terms like phi jk, chi aj, chi dk. That's not even. You have terms like this. So this is the quadratic part of the Yang-Mills Lagrangian. This is a term in the cubic. Now these terms are invariant if you scale chi and chi bar in opposite directions, but this one's not. So as soon as you introduce this interaction term, you break this extra symmetry, this symmetry. Okay, so now I'm going to try to do things in 10 dimensions. So, are there any more questions about 4 dimensions?
But the symmetry that you are saying doesn't exist in the interaction field.
Right.
That actually corresponds to giving the overall phase to the supercharges, right? All of them having the same phase, right?
No, so it changes Q in one direction and Q bar in the opposite. So it's like an R.
But UN transformation, right? All Q's rotate the same way and all Q bars do the same phase, right?
Q and Q bar go in opposite directions. Q and S bar will go in the same direction, and Q bar and S will go in the other. Whereas the projected transformations, the one with YZ, those will commute with these. Okay, any other questions? Okay, so now the idea is to generalize in 10 dimensions, and as I said, there's some partial results, but certainly there's nothing that is as successful as the 4-dimensional case. So I'll discuss 2 different ideas. One idea is just to generalize the lambdas and mu's to 10 dimensions. Okay, so as was shown, I think Houston was the first one to discuss this. Wayne Houston. So the idea is how to generalize twistors to higher dimensions. So let's just do the bosonic twistors. So the idea is that instead of having lambda A and mu A, now let's call lambda alpha mu alpha, and now of course this is a d-dimensional spinor index. And we're going to require that lambda is a pure spinor, which says that there are different ways to say it. If you want to say it in arbitrary dimensions, you can say that this is proportional to the self-dual 0/2 form. So in 10 dimensions, it implies that lambda again and equals 0. And it implies that lambda parameterizes the space SO in Euclidean space SO d over u is the projective part parameterizes this. Another way to say it, so
So
just
you write that U is a linear combination of these gammas, right?
so what
The
that
top
means
line,
is,
lambda alpha, lambda beta.
yeah, so what I mean is, I just need another. So that's what that means. Okay, another way to say it is that you can choose Lorentz frame in which the only component of lambda which is non-zero is the one with all plus. So that's just using this u d over 2, or d over 2 of these indices. So that's another way to say what the pure spinor is. Okay, now mu is also going to be a pure spin, and they're going to be related in the same way as here. So mu alpha is going to be the gamma m alpha beta, gamma beta xm. So one can easily show using the properties of lambda that mu is also a pure spin. And in addition, mu satisfies the property that mu gamma mn lambda.
Okay, sorry. So this lambda belonging to SOD by UD by 2, that's for arbitrary d, is it?
Even d.
Even d. Okay.
Now, in fact, you can show that this lambda and mu fit together into a d plus 2 dimensional pure spin. So this, if I call this ZA, it turns out that ZA takes values in SO d plus 2 over u d over 2 plus 1. So in 10 dimensions, this you can think of as a 12-dimensional pure spin.
So if we contact mu with just lambda alpha,
sorry?
alpha with lambda alpha, if we just contact, then we get a lambda gamma and lambda term that should mention. Why should we introduce this gamma in it?
You're asking me why do I define mu in this way?
No, if this is the expression of mu, then we contract mu alpha with lambda alpha, that will give me a lambda gamma and lambda term.
So it implies that mu alpha lambda alpha is equal to 0, right? But it also implies this one. Okay, so in a general dimension, it will imply, as I said, that mu is actually a 12-dimensional, or d plus 2-dimensional system. Okay, so these are the...
And that ZA will satisfy that first equation for d plus 2 dimensional on that same board. D plus 2 dimensional power matrices.
This one?
The first line.
Yes.
So ZA will satisfy
Yes.
with d plus 2 dimensional one.
Yes. So that makes it obvious that this transforms under conformal transformations, like an SO D, 2 spinor. So in 4 dimensions, this transforms like an SO 4, 2 spinor, which is of course equal to an SU 2, 2. In general D, it transforms linearly under the conformal group. Okay, so that part is easy. That was done probably the early 80s. Now one wants to do super twistors, and that's where life gets complicated. So in 4 dimensions, all we did was add these etas. And that's because the superconformal group is very simple in 4 dimensions. Now, in 6 dimensions, it's also not so complicated, but in 10 dimensions, there's really no useful definition of a superconformal group. So we have the conformal transformations, we have the supersymmetry transformation, but if you try to put the two together, you just get a horrible mess. So what I did in that paper I mentioned was break the conformal invariants, because then after all, superangles in 10 dimensions is not conformal invariant. But introduce fermions in such a way that it leads to supersymmetry transformations transform linearly. Okay, so what I did was introduce not a scalar fermions, but a vector fermion. So instead of having lambda and mu and eta, I had lambda, mu and gamma. And we'll see why.
Historically, twistors were used for conformal theories, right?
Yes?
I mean, is it natural to use twistors even when you break conformal invariants? I mean, why twistors incurred?
Okay. Well, let me say, so pure spinors are obviously there in the 10-dimensional theory. Pure spinors are equal to twistors, so the question is if these spinorial variables, bosonic spinorial variables, are useful in higher dimensions. So there's a little bit of a story with this. So this was started by Witten. So the question is, if you start with the Green-Schwarz, so in one sense I can start with this Green-Schwarz superparticle. So my intuition, which may be not correct, is that in general twistors are not useful if you don't have conformal symmetry, unless you want to do space-time supersymmetry. So I think twistors are actually useful not for describing conformally invariant systems, but for describing supersymmetric systems. What was...
What is that relation with, so far we were seeing twistors more related to conformal invariant, but now you are saying pure spinor is more related to supersymmetry.
Okay, so what was shown already that pure spinors is related to supersymmetry?
Yeah,
That's okay to say. Pure spinors are equal to twistors in the same objects, at least if you ignore this mu. So they're obviously related, pure spinors and twistors. Pure spinors and supersymmetry are obviously related. And in fact, twistors and supersymmetry are related, and that's what I'll say exactly now. So that was the first paper on this that I know of is by Witten. But then it was quickly picked up by various groups, starting with a group from Kharkov. So I'll try to say what their ideas are, and then you can see if you think it makes sense to you or not. But I mean, this is obviously not, since the project has not been completed, I can't prove to you that the end point is where you want to go, but I think the starting point is promising. So obviously, if you want to start in 10 dimensions, you don't start with this, you just start with the ordinary. And what was pointed out was that this action, of course, has kappa symmetry. So the kappa symmetry is delta theta alpha equal p slash kappa alpha. So that's what I discussed. I guess the first lecture. And now, if you think of P as being equal to lambda, okay, you can write lambda gamma and lambda bar. This kind of twistor relation. Then in fact, you can write this as something like kappa lambda bar lambda. But then there are other terms. Okay? This is just one of the kappa symmetries. So the let me try to say it in a
You are
different
now
way.
considering d equal to 10 only?
I'm doing d equals 10 now. See, for me, life starts with d equals 10.
Okay.
So,
And twistors are related to supersymmetry, especially in that dimension?
well, also in 4 dimensions, as we just saw.
Okay.
But the claim is in 10 dimensions, yes. So through kappa symmetry. Not just in 10 dimensions. Wherever the Green-Schwarz string has kappa symmetry, if you just 3, 4, 6, and 10, you can do this. Now, so the kappa transformations of theta can be thought of as transformations where you shift theta by a quantity proportional to lambda, where lambda is a twistor variable. So what this group, so the first people to interpret this way, were a group from Kharkov, including Volkov, who's one of the Russian supersymmetry people, and Sorokin, who's still working on this, is that this can be thought of as a world-line supersymmetry transformation. If you think of theta alpha as being a world-line superfield, let's call kappa the Grassmann parameter, then this transformation here is just a world-line supersymmetry transformation. Now it's just a single one because you only have single kappa. In 10 dimensions, of course, you have 8 independent kappa transformations. But it turns out you can interpret the 8 kappa transformations as coming from a theory with n equals 8 world-line supersymmetry. So the idea was that using twistor variables, you can interpret kappa symmetry as a world-line supersymmetry, a geometric transformation, where the superfields are constructed such that the twistor variables are just the superpartners of the thetas. So that's essentially why twistors are related to supersymmetry. Is that as soon as you have thetas and you want to interpret thetas as variables on the world line or world shape, then the superpartner is some bosonic spinor variable, and it turns out that it has the same properties as a twistor variable. So these ideas were explored at the classical level. At the quantum level, people ran into problems. But for example, Witten showed that integrability along these twistor deformations of theta is related to the equations of motion of the background, which is nothing more than the statement that kappa symmetry implies the background equations of motion. Okay? But one would like to understand the pure Spinor formalism as being somehow some geometrical formalism, and this gives at least some clues about how you could do it. You interpret the BRST as having something to do with world-line supersymmetry. So these ideas seem to fit together.
What did you say Witten showed?
BRST,
No.
so remember Q of theta alpha is just lambda alpha. So in this language it looks like a world-line supersymmetry transformation. So by putting in twistors into Green-Schwarz you get world-line supersymmetry or world-sheet supersymmetry. So people call this the doubly supersymmetric formalism.
Sorry, bar means what?
Okay, so when we were doing the 4 dimensions, this was like lambda A and lambda bar A dot. In 10 dimensions, I didn't say this yet, but these objects have to have their conjugates. So these are the conjugates. And P is going to be lambda again, lambda bar, as it was before. Okay, so this is some motivation for, and there were many groups. Okay, so I already mentioned the Volkov group, Sorokin, the other people are Tkach and Ziltu. So this paper was really the one that got me started in this direction, but this was written in the late 80s. And there was a group by Tony, and collaborators, Paul Howe and collaborators, and Kerry Stell. People were studying this classical doubly supersymmetric action. But they got stuck. they couldn't quantize, so they couldn't do any computations. But at least to show that, for example, that the theory made sense at the classical level, that they were able to do, and extended it to D branes and things like that. And it turned out to be useful for studying classical solutions of supergravity. But okay, that's a different story. I just wanted to say why twistors and supersymmetry seem to fit together nicely. Okay, so going back to this story of 10 dimensions. So, are there any more questions or comments about why twistors and... Okay, so this has nothing to do with conformal symmetry. Okay, okay. So now, let's go back to this. So here, I'm not going to worry about conformal symmetry, but I want to have these lambdas. And I want to have an action of this type. So these should somehow replace the x's in the game. And the way it seems to work is to do something like this. So instead of just having this term, as in the four-dimensional case, we're going to add a term here of this type. So the term we're going to add is of the type gamma slash theta. Okay, obviously we're going to do this so that space-time supersymmetry acts linearly on these. Okay, and we're going to write gamma m is equal to lambda gamma m theta, and pm is equal to lambda gamma m multiplied. So we're not going to try to write the conformal generators because this term here is going to spoil the conformal symmetry.
Now that relation doesn't hold on, is new gamma and lambda equals to 0, that relation that we had previously.
That's right, good. This relation here is now no longer true. So what you find is that mu alpha, lambda alpha is still 0, that's fine. But the second one is now modified. It's mu gamma m n lambda. If you contract this with gamma m n lambda and use the fact that lambda gamma lambda is 0, you find this can be written as gamma n gamma n. So this is the new relational function. Furthermore, because lambda gamma lambda is 0, there's another constraint, which is a gamma slash lambda. Gamma m lambda is 0. Okay, so these are the constraints.
But these virtue the mu alpha lambda alpha equals to 0 still works that way.
This is still okay because lambda gamma lambda and gamma slash lambda is 0.
This is the last formation before.
Yeah, this follows because, that's right, because gamma is lambda gamma theta, so yeah. Okay, so now the thing I have to tell you is what's the supersymmetry generator. The supersymmetry generator is going to be gamma slash lambda bar alpha. I'm not sure at this time, I can check it. I think there's a factor of a half. Sorry, there's another constraint, which is just a projective constraint. So it's just mu, as in all the other theories. If you scale this in one direction, scale this in the opposite direction, it should vanish. So you have lambda mu bar plus mu bar plus gamma. And the action is, of course, the obvious action. In some sense, it's the same action as here. Just the y's and z's are different. So these would be the z's and these would be the y's. Okay, so the first thing to do is to check if the field satisfying these constraints has something to do with 10-dimensional super Yang So that turns out to work nicely. So the fields you can expand, of course, in gamma. But because of this constraint, there are only 5 independent gammas. So instead of having 2 to the 4th terms, like in n equals 4, d equals 4, you have 2 to the 5 terms. So I'll write down what the solution is. So, if you try to solve these constraints, you find that the unique solution has this form.
Sorry. We had just used the convention of calling the lambdas to be z's earlier.
So these are, oh sorry, I should call these z's and these y's, yes?
Does it matter here? Or?
Yeah, I think of these as being the momentum, these as the
Yeah.
coordinates, and I'm writing this in terms of the coordinates.
Yeah.
And I didn't tell you what pi bar is, so
What was the
P is equal to this.
H also. No?
Right. Okay. So Kn is equal to lambda gamma n pi bar. So pi bar is the expectation value of lambda bar. Okay, so in other words, this has a term phi of is equal to times e to the I mu pi bar times delta lambda minus lambda r. So probably I should have called this lambda bar r. Right? So it's the value of, yeah, maybe I should, that would be more consistent with what I have here. So it's the expectation value of lambda bar. Okay, and H is anything satisfying HMKM is 1. So it turns out that because of the properties of gamma and lambda bar, this expression doesn't depend on H, it only depends on the normalization of H. Now A plus and A minus you can think of as different components, well they are different plus A plus, where these satisfy different constraints. A minus slash lambda bar equals 0, and A plus slash lambda equals 0. So they,
So what is lambda r?
okay, so lambda is just the value of this twisted variable.
Oh, okay. But
Lambda
the
bar
particle input.
is the expectation value of this. So when you hit it on the, if you like, if you write it in Fourier space, it's the thing which contracts with mu. So the d mu is lambda bar. Okay, so and the fermion splits up into these components. So if you take S alpha, which is the gluino, then it splits up into lambda alpha S plus so the 16 components of the gluino split up into this one, I guess there are 10 of these and one of these. So of course, S alpha has only 8 physical components on shell. Okay, so one of them sits here, 6 of them sit here, and one of them sits here. Okay, so it has not so different form from here. I mean, it's a little bit more complicated.
So E plus got contracted with lambda r.
I'm sorry?
That those equation A plus that's contracted with lambda r or lambda.
Second term. No, the line above at the end.
This is A plus slash lambda. So it's A plus m, gamma and lambda.
Oh, there are no lambda r.
Well, lambda is a coordinate, so lambda is equal to lambda r because of this. So this, in some sense, splits the polarizations of the gluon into those polarizations which are in. Let's just do an example. Suppose lambda is a pure spinor in the direction this. Okay? Then what A plus is, because it has to contract with lambda to give you 0, it means that the non-zero components of A plus are A1 plus IA2, A3 plus IA4, and not A0 plus I. In other words, lambda splits the SO10 down to U5. Under that split, an SO10 vector splits into a 5 and 5 bar, and this is the 5 and this is the 5 bar. And similarly, it splits the SO10 spinor into a 1, 6, 1, 4, and 4 bar, and this is the 1, 6, and 1. So in some sense, this is the U5 version of this, which is U4. So, okay, so this, up to here, it's possible to do something. Now, the next thing you want to do is to compute scattering amplitudes using this. And that, I don't know how to do, but there's one nice feature which I should mention is that this superfield here is closely related to the superfield that Carlos was discussing. So, the superfield here, first of all, it turns out to have projected weight plus 1. So that means, so this had, remember, projected weight 0. This one, if you see what the projected weight of these S's and gammas are, you'll find that this has projected weight plus 1. And in fact, it's equal to lambda alpha A alpha. If you write these mu variables in terms of x and theta in this way. So it's related to the unintegrated vertex in pure spin. So this is it. Mu equals. So as in what tells us that if theta equals 0 for in theta, in the gauge, I should say one more thing. So Carlos was mentioning this gauge here for A alpha. In this gauge, the 0th order component of A alpha, the component with theta equals 0, is 0. In this expansion, the component at 0th order in gamma is not 0, it's affirmative. So in fact, this is not the gauge that we're going to use here. The gauge that is relevant here is so it's I don't know what the right word is. It's something like a supersymmetric Lorentz gauge. So there's another way to write it, which is using this polarization H. You can write the gauge field in terms of the field strength in this way. So remember that if you're doing Lorentz gauge in ordinary electromagnetism, you can write the gauge field in terms of the field strength in this way. Because you contract this with momentum, that just gives 0 because of the equation. So there's a supersymmetric version of this, which relates A alpha with the field strength, whose lowest component is the gluino. That's, in that case, this is equal to this one. Okay, so by using this to compute the amplitudes, it might be possible, I just don't know how to do it.
Here, H is the momentum.
HM is any vector satisfying H dot K is equal to 1. So if this was the momentum, this would just be vanishing because Km Fm. So this is, if you choose, for example, H to be light-like, so just to be in the, then this would be light cone gauge.
So that Kn is non-zero.
Which one?
Kn.
KMAN is 0. Because, again, KMFMN is 0.
So, did you say something about the helicity plus and minus being related to the 5 and 5 bar?
Yes. So these are, this, it's not helicity, in 10 dimensions don't have helicity, but I want to separate the blue one into those polarizations in the 5 and 5 bar.
But then, is the separation meaningful for, say, when you want to go to 4 dimensions in dimensionally reduced?
So it's not true that this, if you dimensionally reduce to 4 dimensions, lands on this. That's obvious because this is fermionic. The lowest component is a fermion, and the lowest component of this is a boson.
Okay, but say, suppose you are in 10 dimensions,
Yeah.
and you have the 5 and 5 bar.
Yes?
And then you say, well, this is related to LST minus or plus. And
Yes.
then you dimensionally reduce whatever you have in 10 dimensions to 4 dimensions.
Yes.
Is separation in plus and minus preserved under this dimensional reduction?
Okay, let's see. So suppose you restrict the momentum polarizations to be just in 4 dimensions. And I think the answer is yes.
That's great.
Yeah, because it's just plus plus or minus minus. And that is just the. But, okay, you asked me a question, I answered it in 5 seconds, but the chance of it being right is, let's say, 60%. Okay.
I usually believe you.
Well, you should, but okay. Okay, but anyways, it's something for you to think about. Okay, so that's what I wanted to say about that, and that's, I mean, I haven't gone any further than that because I don't know how to compute the amplitude. So the last thing I have 7 minutes, is it? Okay. So there's a 10-dimensional version which was not started by me, it was started by Mason and Skinner, based on some work of the group of Ferry Cachasso, which is, so, Mason and Skinner are twistor people. So they were, Mason was the student of Penrose, Skinner was the student of Mason. But, so everything they do, they call twistors. But I don't really think what they're doing is twistors yet, but maybe they see something, so they see something in different ways than I do. But, so let me write their action, and you can tell me if you call it twistors or not. So their action is, it's just as stupid as the action I wrote down for the twistor thing. The only difference is that if you take the ordinary particle action and just replace dot with d bar x and add d squared, that would be the ordinary particle written as a string action. Now suppose you also add, they did it in the RNS formalism, just because I don't have much time. Just assume you can do RNS, and I'm going to do pure spin. So you do the same thing for the P's, and for the W's. So now it looks very much like pure spinners if I had done the right movers like this. So this would have almost been the pure spinor action. The only difference is that I would have to replace this with dx. Here's the pure spinor action. So what they do, what I did based on what they did, is just replace this with p and make all of these holomorphic. So it's essentially that n equals 2 superparticle, replacing all the dt taus with d bars. Now it's easy to show there's no central charge.
It has both left and right sectors.
Everything is left moving.
But it has both p and p hat.
Yes, so it looks like it should be, this should have been right movers.
It's just doubling of the same thing.
So your question again is, well, why don't you put in the right movers? Okay, so they don't do it. I don't do it. And now, okay, it's easy to show the action is still conformal invariant. Q is going to be lambda alpha d alpha plus lambda hat alpha d hat alpha. But again, everything is left mover, so this is all dz. And d alpha is actually simpler than before. It's just p alpha plus p slash theta, with no dx's or d thetas. So in some sense, it's a simplified version of the pure spinor action. And furthermore, now you can see that if you tried to put an alpha prime here, I could get rid of it, because I can rescale x and all these variables so that alpha prime can be removed from the action.
So this conformal invariance now, theta, the hatted variables will have different conformal charges.
No, everything is conformal. These are all conformal weight 1, 0, and these are all conformal weight 0. So there's nothing which conformal weight 0, 1.
Oh, so del bar or del matter.
So everything is del bar. So the central charge for the right movers is trivially 0 because there's nothing right moving. And for the left movers, essentially it's 0 because, well, the sum, before all the right movers are now left movers, and before they had central charge 0, so 0 plus 0 is still 0. Okay, so far it's trivial, but now you can write down vertex operators. And the vertex operators with respect to this BRST operator. So first of all, you can only write down massless vertex operator. That's easy to see
So is
because
it supergravity?
this is going to give you supergravity.
That's why you have theta and theta hat.
Yeah, so it's technically. So the vertex operators can't have any negative conformal weight because x with x has no OBE. So this object here has dimension 0 independent if k squared equals 0 or not. Okay, so you can't build anything of negative conformal dimension, so if you want u to be of the right conformal dimension, it has to be massless. So the vertex operator is just PM. Now you might try to put in a term with d theta here, but you'll find it, if you tried to put it in, it would not be BRST invariant. Okay, so that's the vertex operator. And there's one more thing I have to say. So the one thing I have to say is that the vertex operator,
N is constructed the same way, which has
sorry,
N
N is the same as before, W, gamma, M, and lambda.
and it has the W hat also.
Sorry, you're right. This is the open. If I'm doing the closed, it's the same thing
With the hat.
with the hats, yes. So you have both N and N hat. Thank you. And the supergravity vertex operator is the, like, you did discuss this, right? The closed vertex operator is just the left-right product of the open.
No, I think
Okay, but okay, I don't have time to do that. It's just like in bosonic string theory, where now the point is that in order for this to be consistent, you need the p squared. You need to impose the Virasoro constraint, which is just PM. Now in this case, PM is just equal to KR over Z minus CR. It's easy to see this just because the only thing P has poles with are these exponentials. Doesn't have poles with anything here because these only involve P's and not X's. So P squared equals 0 implies, it's not difficult to show, that KR dot KS over ZR minus CS sum over S is equal to 0 for every R. This is the scattering equation. So what is claimed and has not been shown is that if you compute scattering amplitudes of these vertex operators, where the locations of these vertex operators are fixed by this equation, you reproduce the supergravity scattering amplitude. So again, it's like what we saw in 4 dimensions. The vertex operators are not integrated. They're just fixed at certain points.
So that version has not been shown?
It has been shown.
It has been shown.
So if I understand correctly, Umberto Gomez and Alice Swan. You want? Alice?
You want.
You want, sure. So,
It has been shown that this scattering amplitude reproduces the known ones.
right. So what was shown before that was Mason and Skinner based on work of Cachasso, Yuan, and Heat. Showed that the RNS version of this reproduces at least the Neveu-Schwarz scattering amplitude. So this was trivial extension to pure spin. So again, it's a mystery why this works.
Okay, but for arbitrary and
Arbitrary endpoint scattering, yes.
yeah, but that has a lot of techniques involved, as was shown in Carl's lecture.
Yes.
Right? So in that compact form, it is coming out to be that compact form.
Yes. So again, I don't know how to generalize this to loops. I don't know how to connect this to the ordinary string. So this is almost the ordinary string, right? It's just I turn some right movers into left movers. I change some dx's into p's. I fix the positions of the external states, and I get at delta prime. I get the same amplitudes at delta prime equals 0. I have no idea how to show that directly. So that's a mystery, and if anybody figures out why this works, that would be a big clue of generalizing this to, well, possibly generalizing this to the full solution. Okay, so that's all stuff.
This last question can you respond to it?
Yes, sir.
That what case PM will be taken to 0.
This equation? Yes?
So it should be KR by Z minus ZR and KS by Z minus ZS.
I don't understand the question, but this is KR dot.
And he's asking, how does it come from PM to PM equals?
Let's do it. So this thing squared, it has to be 0 for every value of z. This is supposed to be 0. So let's choose z to be close to zr. So this thing will just go like kr over z minus cr, okay, plus terms which are not. Okay. And this term will go like, so you have to use the kr squared to 0 because it's massless. So this will give some s different from r, ks over zr minus ds. So if this is going to be 0 near z equals zr, then it's clear that this thing, in order to not have a pole, it's clear that this has to be vanishing. So for every r, you have to have the property that kr dot ks over zr minus ds.
Sum is over S not equal to R.
So yeah, when s is equal to r, it doesn't contribute because kr squared is 0.
And this PM equals to that is coming from
So the vertex operator, the only dependence on x in the vertex operator comes from here. And P only has poles with x. So that's why it's just.
And this only gives P theory because all vertex operators are constantly massless.
Yes, there's no, well, I don't know how to generalize this to massive states. And in this description, all the vertex operators are massless.
But the action is a two-stringy like action, but the vertex operators are only massless.
That's right, the states in cohomology are only masses, and I should say, the action also is independent of alpha prime, just because you can rescale the field to get rid of alpha prime. So in some
Cohomology is
sense-
also massless.
Cohomology is also massless.
Yeah. Now you could ask, well, why doesn't this work for bosonic string? So suppose I just did this. You could ask, well, what do you get? You don't get gravity. You get, again, the vertex operators do have the same form. They look like gravity vertex operators, but when you compute amplitudes, you find instead of starting with, so what you want is something like r plus, what could you get? You could either get r or you could get something else. You can't get r plus alpha prime r squared because here's an alpha prime. So what you get when you do the bosonic string theory, I think you get r cubed. And when you do heterotic string, I think you get r squared. Only with type 2 do you get what you want. So,
You see, it's not just, it starts at order R cube. There's no R term.
there's no r term. So, the cubic vertex is already has, I guess, 6 derivatives in it.
Conformal gravity.
It's not conformally invariant. Well, maybe 6 dimensions it is, right?
It's a conformal gravity.
So, maybe it's related to conformal gravity in some funny dimension.
But it's not Einstein either. I mean, there is
No, no,
It's
no.
not Einstein, however.
It's not actually.
So, okay, so supersymmetry is somehow playing an important role. So this, it's only in the maximally supersymmetric case that you get what you want.
And the bosonic string is after adding BC goes to everything, right?
No, here is also BC goes there.
Now there is a conformal
BC goes will be always there. Otherwise,
Yeah, there's always all through.
Yeah, in pure spinors there's no BC ghost because there never are BC ghosts in pure spinors. But when you did the bosonic string, yes, it would just be this action.
And in RNS portion also there will be BC goes.
Yes. So you just have BC and then you have usual gamma m bar gamma n, but if you do type 2, the gamma half would also be d bar.
Central charge will match.
And you also have to add the beta gamma.
Yes.
Central charge will match in every of such cases.
I'm sorry?
Central charge.
Yeah, the central charge is all, you never have any right movers.
Yeah, but P del X, what is the central charge? That is the same as the del X del X?
So P del X is the same, like, so it has, okay, so let's remember dx d bar x has central charge c equals 10 and c half equals 10. This is the left mover and right mover, right? This one has c left equals 20, c right equals 0. Because you get 10 something right.
So then with BC ghost, how does it match? Only with
So you
BC
get
ghost, boson.
You get b d bar c and also b half d bar c.
Okay.
So the right movers are left movers. So
Okay.
instead of getting minus
Oh.
26, now you get minus 52.
Yeah.
If you're doing close, if you're doing bosonic string, you get 26.
No.
In bosonic string, m is 1 to 26. So there's no conformal number, but the theory doesn't compute.
So all the central charges are double.
I'm sorry?
All the central charges double.
Yeah,
One
the
side,
left
one
mover is
side.
double, the right mover is 0.
So beta gamma also there are two sets of betas and two sets of
Yeah, if you're doing type 2, yeah. Yeah, so only the type 2 works like you want. The others give you some funny theory.
But these BCs don't come from some diffeomorphism nature.
So there are attempts to get this from some ordinary looking string theory. I can't say the attempts are wrong, it's just, they're not straightforward. So, yeah, it's a funny starting point if you try to get these engaged.
It can be viewed as a complexification of the superparticle action.
Yeah, that's right. That's how I view it. They call it some Twistors thing, but I agree with you. I think it's not, that's good. So one point I should make, which is Twister-like, is this constraint here is identically solved in the Twister theory. So once you write PM is equal lambda gamma and lambda bar, if your Zoe constraint is identically solved. So that's why the Twister theory always puts you on the scattering equilibrium. So that aspect is certainly Twister-like. But the vertex operators are functions of x is not the Twister.
Let's thank Ethan for his excellent lectures.
Scattering amplitude description is like Twistors.
It does look like, yeah, because the action is like, it's a chiral action.
That's right.
So that's the same type of action as Twistors. But Twistors are not directly, variables are not.
Twistors are also related to some concept of complexification.
Well, that's the way they think about it. That's right. But it's not the way I think about it. So that's right.
After, it may be looking like your action.
Huh?
It looks like your action.
My action.
What you were doing yesterday, like with only they.
No, I didn't write that action.